So let's talk about the nephron. Okay. The nephron is the functional unit of the kidney. And this is what I'm going to draw up here. It's microscopic. This is where it gets a little bit more crazy for you guys. I think just understanding what a kidney is macroscopically, like if I've seen it with the naked eye and the ureters, that's the easy part. But now we got to look at it microscopically, and we got to draw this whole thing out for you. So we have 1 million of these suckers in each kidney. All right? So let's draw this thing out. And this is all about the models I'll show you once I get all this up here. This is going to be your afferent arteriole. And again, I'm going to just abbreviate to speed up time. All right? That's going to lead to this network of capillaries known as a glomerulus. Okay. And then you're going to have the efferent arteriole here. Okay? Now everything I'm going to draw in black is going to be the nephron. The glomerulus is not the nephron. It's just what's going to feed things into the nephron. Okay? The first part of nephron is this little helmet, or strainer is what I call it. We call this Bowman's capsule. Again, you wouldn't abbreviate, I'm just speeding it up. Bowman's capsule is a big strainer. And you learned a little bit about Starling's forces with oncotic or osmotic pressure and hydrostatic pressure. It's going to come back, and it's all being dealt with again here. So you got to go back to the circulation to understand that concept. But what's happening over here is what we call filtration. Fluids are going to go into the nephron, but big stuff is not going to go in there. Red blood cells, proteins, but water and electrolytes, those will. Now we got to create a pressure to push that in there. This is a strainer. If you're going to, just look at this. If you take a pot of spaghetti and you're boiling it with water in there, and then it's boiling, and now you've got the strainer in the sink, you're going to take the pot over here, pour it right into the strainer, put this pot over here, take the strainer and put it on your dish. What are you going to have in your dish when you do it that fast? You'll have noodles and what else? Water, okay? You'll have water in there. The reason why you have water is because when you took the strainer, you didn't do this with that face, all right? You have to do that because when the noodles come up and they come back down and you grab it, you create this pressure. It's either you do this kind of thing with that face, and you all do that face, put a mirror in front of you, you know what I'm talking about. But the other thing you could do is when they're not looking, you take your hand and press, right? You've got to create a pressure to strain out all that water, okay? So this is what we've been talking about. High blood pressure is bad for you, but low blood pressure is bad for you equally as important. If you don't have a strong enough pressure to push out all this extra stuff into the nephron, then it's going to stay in your bloodstream. Does that make sense? That means all your salts were supposed to go into the nephron to get rid of the excessive amount of salts, but now the salts are going to stay in your body. Or let's say they're toxins, or let's say ammonia or something. Now the ammonia stays in your body. So we have to have pressure to push that fluid into the nephron. So the function of Bowman's capsule is filtration. And the type of epithelium that would be found there, what epithelium causes filtration? Simple squamous epithelium. See, chapter 4. See, you're coming all together. Now, the fluid goes into the nephron. Now this fluid is known as filtrate. Okay, so we refer to it as filtrate. It's not urine yet, it's going to make urine, but as it's in this nephron, it's known as filtrate. Now, the next part of this nephron kind of goes like this. This is called the proximal convoluted tubule, or PCT. Now, before I tell you about the function of this, understand that the efferent arteriole goes back into capillaries, which makes sense. Arteriole goes to capillaries. These capillaries, and I'm not going to draw it on my picture here because it would just mess things up and confuse you, but understand that these capillaries, after the efferent arteriole, these capillaries are going to go all along these tubes that I'm drawing here. So these capillaries are called peritubular capillaries. And they're going to ride alongside the tube. Now, when it filters this fluid into the nephron, it filters most of the fluid. Salts, water, most of that. But most of that stuff is going to get reabsorbed. Reabsorbed means that the fluid or anything is going to go from the tube to the capillary. You see what happens here, how much of the fluid gets filtered by the Bowman's capsule is 200 liters per day. 200 liters. That does not mean you're going to pee 200 liters, otherwise you'll have a bladder like a hamster and you'll run back and forth to the bathroom. You don't pee 200 liters, but per day you are going to have 200 liters going through the kidneys. How much of that actually goes out into your pee, your urine, is less than 1%. So we're looking at 1 to 2 liters per day, depending on the foods that you're eating and the exercise that you're doing. But we're only looking at about 1 to 2 liters per day you actually are going to pee out. That leaves 99% going where? Back to the bloodstream. Okay? So how does it get back up there is what we call reabsorption, going from the tube to the capillary. We'll be using these words quite often. But there's also some things that didn't make it through the filtration area that continue into the efferent arteriole. Extra salts and things. So there's going to be times that we're going to talk about where things can go from the capillary into the tube, and this is called secretion. Okay? So we have filtration, reabsorption, and we also have secretion. And then we got excretion, which is actually going out in the urine. Okay, does that make sense? All right, I'm just going to erase this thing over here for time being. We'll keep more stuff here. We okay with understanding of reabsorption? It's reabsorption, not absorption, because it's going back to where it came from, so it's reabsorption. All right? In the small intestines, it's called absorption because those nutrients never were in the bloodstream in the first place. So that's where that comes in. Okay, the proximal convoluted tubule. What does it do? This is where 65% reabsorption occurs. Most reabsorption occurs in the PCT. That includes 100% glucose reabsorption and 100% amino acid reabsorption in a healthy person, not somebody who has diabetes. All right, we're talking about in a healthy person, 100% of the glucose and 100% of amino acids gets reabsorbed just in the PCT. But 65% of everything else, 65% of your water, 65% of your sodium, your potassium, magnesium, that'll all get reabsorbed, at least 2/3 of it, by the PCT. Remember, we're only going to have less than 1% go out. So we got to somehow reabsorb 99%. So most of it gets reabsorbed by the PCT. Okay? All right, now, so far so good? All right, now we have this loop. This is called the loop of Henle, not Henry. And there's a few parts to this you got to understand. There's a thick descending limb, a thin descending limb. I call this a hairpin turn. A thin ascending limb, and a thick ascending limb. Okay? And these could be very long, and things could be very short, but there's a loop there. Now let me ask you this. If 120 milliliters enters the, and this is a type of A&P, like lecture exam question she could have. If 120 milliliters of filtrate enter the PCT, how much enter the loop of Henle? Well, it took math. You had to take math in order to get into A&P 1. This is just simple high school math. 120 enter the PCT. Then how much is, and you don't even need calculators for this, but how much is going to enter the loop? How much is going to be reabsorbed of the 120 milliliters in the PCT? 65%. So what's 2/3 of 120? Break it up to 3 ways. 80. So 80 milliliters gets absorbed this way. So how much is going to enter the loop of Henle? No. If 80 gets reabsorbed out of 120, 40 enter here. You see? Easy math. There's more math in A&P 2 than there is in A&P 1. But you got to do basic math on here. Does that make sense, how I came up with that, right? 2/3 of 120, just break it up into 3 ways. 40, right? All right, now, the filtrate that is now in the loop of Henle is basically 2 different things now. All right? We have water and we have electrolytes, okay? So we can have, and we still got to reabsorb stuff. So there's going to be water that's going to get reabsorbed, and there's going to be electrolytes. Sodium, chloride, magnesium, potassium, calcium. I'm not going to write them all. I'm just going to abbreviate by saying sodium chloride. But there's a lot of electrolytes. As the filtrate goes down the descending limb, water gets reabsorbed, but the electrolytes do not, or very insignificantly. So let me ask you this. As this goes down further and further to the hairpin turn, is the filtrate getting more dilute or more concentrated? All right. getting it. Okay, let's just hope it's because it's 8:30 in the morning. If I have, let's talk about food, okay? Food usually works for people. You have lemonade, you got water, and you got crystals. I'm removing the water, but leaving the crystals there. I taste it. Is it going to be more bitter or more dilute? Bitter. So again, I ask you, as this goes down inside the tube, is it going to get more concentrated or more dilute? See, food works. It always does. Okay? So if these loops are very long, do you understand that the filtrate will become more concentrated than shorter loops? Okay? That's what you got to deal with in lecture. You got to understand that concept. I'm just giving you an overview of stuff. Okay? Now, by the time it goes down to the hairpin turn, another 15% has been reabsorbed. So we have a total 80% reabsorbed. Do you see how I got that? 15 plus the 65?
And reabsorption just means that it's
going back into the bloodstream.
We're following, it's leaving, it's popping off.
It's going back into the bloodstream.
Right.
Okay? We're doing okay, because by the time we get to the end, we got to have less than 1% going out there. We only have 20% left. Does that make sense? Now, going up the loop of Henle, we still have water in there, and we still have all the electrolytes. But there's a difference now going up. As it ascends up, it's impermeable to water, but the sodium and chloride do get reabsorbed. So as we go up, is the filtrate getting more concentrated or more dilute? Dilute. Okay? So far so good? Then we have another part that kind of zigzags like that. This is called the distal convoluted tubule. And at this point, there's going to be fine-tuning going on. Most of the filtrate has been reabsorbed, 80%. So now there's some fine-tuning going on. If I had a glass over here and I want to fill it up with water, I need to get it right to the brim. And I'm going to go turn on the faucet full blast. When I get to maybe an inch away from the brim, I'm going to slow it down, right? Does that make sense? I'm doing the bulk first, and then I got to fine tune at the very end so it doesn't spill over. That's what's going on over here. We reabsorb the bulk first, and now we got to really determine what we need to reabsorb or secrete. The only way this can do that is that the nephron needs to talk or communicate with the blood vessel to see what is in the blood vessel that we really need to put back. We know we need to put most of the stuff back, but now what exactly do I need to put back just to make it more, conducive for you to walk around and stuff? So this part here is actually going to, and we'll talk about it later, but this part here is going to get twisted and it's going to touch one of the blood vessels over here to communicate, to see what's going on, what do we need to really put back. So we have fine-tuning that's going on here. And we have a hormone, that's going to target the DCT. What's a hormone that we learned that targets the kidney? What's that? ADH. What's another one? Because ADH we'll get to. It's not this one over here. What's the other one? Comes out of the adrenal cortex. You See why you have to go back to old stuff? Remember good old aldosterone? Okay? Aldosterone, that's what I'm saying. Aldosterone is going to target, now you can't say kidney. Now you say it targets the DCT, the distal convoluted tubule. What does aldosterone do? Reabsorbs, and here. More specific though. Sodium. It reabsorbs sodium, but it secretes what? Potassium. Alright? How does it know how much? Well, that's what I'm saying. The DCT has to talk or communicate with the blood vessel to determine that. And we'll get back into that. Then this DCT is going to go into another tube. These are called collecting ducts. And we have a lot of DCTs going into collecting ducts. So there's a DCT from another nephron, a DCT from another one, a DCT from another one, a DCT from another one, and so forth. There's a hormone that's going to target the collecting duct. What hormone is that? That's the ADH. Antidiuretic hormone, also known as vasopressin. What does ADH do? It or reabsorbs it. Now we're going to use words reabsorption versus secretion. You're right, it's retained in water. So what is it going to do? ADH, as the name implies, diuresis means to pee, right? To lose water. But this is an antidiuretic hormone. So therefore, if this area is flooded with ADH, then we are going to massively reabsorb water. If we have a lot of ADH here, what happens to the volume of your urine? Increase or decrease? Decrease. What happens to the concentration of your urine? It's only going to reabsorb water, so it's going to leave the electrolytes in there. So what happens? All right, let's go back to the lemonade thing, all right? You have the water, you have the crystals. I'm just going to reabsorb the water. What happens to this stuff I'm going to throw out from the pitcher? Is it more concentrated? See, it makes sense. Okay? So if this is flooded with ADH, you're going to have a concentration of your urine, but the volume will be decreased. If we don't have much ADH over here, what happens to the volume of your urine? It increases. What happens to the concentration of your urine? It decreases. Don't memorize it. You should be in this field now where you should be able to understand the concept. Where does ADH come from? What organ does it come from? Posterior pituitary. So you have this posterior pituitary, there's the anterior pituitary. So you're going to have ADH come out of the posterior pituitary. There is something that some people like to imbibe that's going to block this from occurring. What is that? That's alcohol, right? Or ethanol. Alcohol is going to block ADH from coming out of posterior pituitary. So are we going to have this area flooded with ADH? No, there's not going to be any ADH coming out. So if there's no ADH over here, what happens to the volume of your urine? It increases. Does that make sense? And you get dehydrated. All right, you see how you're understanding this concept? And how much, normally, not with the alcohol, but normally how much comes out of here into your urine is going to be less than 1%. Depends on how dehydrated you are, how much fluid is in there, but it's about less than 1% to 1%. Okay? Does that make sense? It's big, but that's a good overview of this whole thing. Now I got to do some other things to introduce you to the different parts of these models, which we'll do in a moment. One other thing I want to mention to you is this here. When we put the glomerulus and the Bowman's capsule together, this is known as the renal corpuscle. So when you read it in your book, that's what they're talking about. It's the Bowman's capsule and the glomerulus together. We refer to it as the renal corpuscle. Okay? Now, that's how it looks for when I draw it. It's much easier for you to understand it this way. But in actuality, it's all mushed together. You got a million of these suckers in each kidney, so they're all crumbled up together. So there's the glomerulus, there's Bowman's capsule, there's the PCT, the loop of Henle, the DCT going into the collecting ducts. Okay? So the filtrate, as I explained to you, we have 200 liters that get filtered per day, 99% gets reabsorbed, 1% goes out in your urine. Okay. Now, two types of nephrons, all right, in general. We have something called cortical nephrons, and what this is that the renal corpuscle, these, will be nearest the cortical, or the nearest the renal cortex, and I'll show you what I mean by that. The loops of Henle go into the medulla, but they're not very deep. And most of our nephrons are like this. The picture will make more sense, all right? 85% of our neurons are like this. Then we have the juxtamedullary nephrons. Juxta is just a fancy word for near. So what they're saying here is these are nephrons that are located near the medulla, okay? So all the renal corpuscles, they're all located in the cortex. It just happens that these juxtamedullary nephrons, the renal corpuscles, are very close to the border of where the cortex or the medulla is. And these have very long loops of Henle, which means that these are the ones that are going to give big contribution to making your urine most concentrated. Remember how I said, if you've got long loops of Henle, then that means that your urine is going eventually be very concentrated. Does that make sense? Okay? So this is what I mean by that. Here's the cortex up here of the kidney, and this is the medulla. So here's a cortical nephron. You see how the renal corpuscle is up here? It's still in the cortex, but the loops don't really go that deep in the medulla. And then this accounts for about 85% of all the nephrons. But there are 15% where the Bowman's capsule and the renal corpuscle is very close to the border between the cortex and the medulla. See it? In these cases, the loops of Henle are very long, and they're contributing to the concentration of the urine. Okay? Make sense of that? Pretty straightforward, but you'll see those words happen. Okay? These are the substances that go into the filtrate, that get filtered by the kidney. Things from protein metabolism, you learn about urea and uric acid, creatinine from muscle contraction, that's going to come into your lecture too. Drug metabolism, stuff that are inactive that aren't really going to do anything, we need to make anything with charges, sodium, potassium, calcium, that all goes in there too. glucose, amino acids, vitamins. Notice things as much as what goes through there, note what doesn't go through there. Red blood cells, white blood cells, the albumins and proteins should not go in there. You should not have blood in your urine. You should not have proteins in your urine. If you have proteins in your urine, then there's maybe the holes of the Bowman's capsule are just too big. You'll have a disease there that's going on. Okay? You should not have proteins in your urine. It produces a foam when you pee. You'll have this foam that appears on top of the water. That's usually a sign that there could be proteins in your urine. Okay? So the filtration, reabsorption, and secretion, things I just explained to you. All right? If we take this even stretch it further out, you have Bowman's capsule up here, here's the capillary, and here's the tube. So you'll have filtration up here. Now it's filtrate. If it goes from the tube to the capillary, it's called reabsorption. If you go from the capillary to the tube, we call it secretion, and everything that comes out is going to be excretion. Okay? Remember how I said the blood vessels, the capillaries are going to be all around here. I didn't want to draw because it would mess up my picture. Here's where you could actually see it a little bit better. All right? You have these peritubular capillaries going all around here. Now, I also want to mention to you for your reading for lecture that if the capillaries are around here, we call them peritubular capillaries. However, when they are riding alongside the loop of Henle, it has a special name. It's called vasa recta. And all I got to say is when you read that, spend extra time reading that, because that's where students really get confused about things. Things called the countercurrent mechanisms. There's a countercurrent exchanger and a countercurrent multiplier. It's countercurrent because they're going opposite ways, and even the blood, the way it's set up is that the blood goes this way, but the filtrate goes this way. So over here, filtrate's going here, but blood is going up here. They're countercurrent. And they talk about how the fluid or the electrolytes go from one place to the other. Most students find that the most thorniest of all of urology. So it's way over the scope of explaining it here in lab. Okay? Questions about this so far? All right, giving you heads ups about this so you could figure out how you're going to, plan your weekend. Okay? So this is just reiteration of what I just did over here and pointing out the highlights. Okay?